Welcome back to the deep dive. For, gosh, over 100 years, civilization has run on this rhythm, this steady beat of fossil fuels. Predictable, powerful, kind of like big drum machines.
Yeah, very loud, very dirty drum machine.
Exactly. But now, we're deep into this whole new era. Renewables, solar farms stretching out, massive wind turbines spinning. It's impressive, it's clean, but, well, the rhythm's different, isn't it? It's much more unpredictable.
And that unpredictability, that erratic pulse, that's the core issue. Our electrical grid, the one we've relied on for decades, it just wasn't designed for that kind of volatility. But what our research shows and what we're diving into today is this quiet revolution happening behind the scenes. It's trying to fix that volatility. And a huge piece of it centers on this one kind of remarkable piece of hardware, Tesla's Megapack.
That's it. And we need to be clear, this isn't the battery you might have seen for home backup, the Powerwall. We're talking huge utility-scale systems. People are calling them the silent conductor of this new energy symphony.
Right.
So our mission today, for you listening, is to get under the hood. Not just what a Megapack is. I mean, okay, it's a battery, but why it's becoming this linchpin, why it represents this fundamental merger of old-school mechanical power concepts with really sophisticated digital brains.
Yeah, and if you want the headline right up front, Tesla's own energy division puts it pretty plainly. They say, essentially, Megapack will carry a lot of the world's load in energy as it allows power plants to run continuously. That's a big claim.
Huge.
But the real magic, the sort of secret sauce enabling that, is something called the grid-forming inverter. GFM. That's the technology that's absolutely crucial for keeping the global grid stable as we add more renewables. It's what makes these big batteries more than just storage.
Okay, before we get lost in the tech, let's just nail down the sheer size of these things. For anyone not familiar with utility-scale storage, how big are we talking?
We're talking seriously big. The Megapack is Tesla's main offering for utilities, for grid operators. It's a BSS, that's Battery Energy Storage System. They build them to be modular, you stack them together, but each individual unit, it holds up to 3.9 megawatt hours of energy.
Okay, 3.9 milliwatt UH.
Yeah.
And in terms of power output?
It can deliver 1.9 megawatts of power.
Right.
So MWH is energy, how long it can run for. MW is power, how much it can push out at once.
Got it.
And just to give you that sense of scale again, your home power wall might keep your fridge and lights on during an outage, right?
Yep.
A Megapack, or a whole farm of them, is designed to do things like stabilize the electrical frequency for an entire city, or soak up gigawatts of excess solar power during the day and feed it back precisely when everyone turns their air conditioning on in the evening.
So it's the bridge, the essential bridge between nature's unpredictable schedule, sun, wind, and our civilization's constant, non-negotiable demand for power.
Exactly. It smooths everything out.
And that smoothing act, that stabilization, it's revolutionary because the old system was built so differently. So to really get why this GFM stuff matters, we have to understand the system it's fixing. Let's dig into that in section 1. The fragile grid and the birth of digital inertia. What made the old grid tick?
Well, its stability came from its history, really, a century of mechanical engineering. Modern power grids grew up around massive fossil fuel power plants, coal, gas, nuclear sometimes too. And the generators in those plants, they had these enormous spinning turbines and rotors, just huge, heavy pieces of rotating metal.
Like giant flywheels.
Precisely. And all that spinning mass, tons and tons of it, created something called mechanical inertia. It's just physics. An object in motion wants to stay in motion.
And that inertia acted like a shock absorber for the grid.
Exactly. It was the grid's natural stabilizer. If, say, a big factory suddenly shut down its machines, or if one power plant tripped offline unexpectedly, the sheer kinetic energy stored in all those other spinning generators across the grid would resist the change. It would slow down the frequency drop or the voltage fluctuation.
Giving the system time to react.
Yes. Precious milliseconds, sometimes even seconds. Just enough time for the centralized control systems to kick in, maybe reroute power or tell another plant to ramp up and prevent a small hiccup from cascading into a major blackout. Stability was literally built into the physical weight of the system.
Okay, so that's the old world. Stable, heavy, predictable. Now, bring in the renewables. What's the problem?
Well, here's the paradox. As we, quite rightly, shut down those big polluting fossil fuel plants, we're removing those heavy spinning machines from the grid, that mechanical inertia. It's vanishing.
Okay.
And renewables, like solar panels and wind turbines, they don't connect to the grid through giant spinning machines. They use power electronics, devices called inverters.
Right. To convert the DC power from the panels or turbines into the AC power the grid uses.
Correct. But here's the catch. The vast majority of inverters installed today are what we call grid following.
Following, what does that mean?
It means they're passive, in a sense. They need to sense a stable, existing electrical signal on the grid, a steady voltage and frequency, that 60 hertz hum in North America, 50 hertz elsewhere. They follow that signal. They can't operate safely without it. They can't create it. They are followers, not leaders.
Ah, I see. So take away the big spinning machines that created the stable signal.
And the followers have nothing reliable to follow. Without that flywheel effect, even small disturbances, a sudden cloud cover over a huge solar farm, a big gust of wind dropping off, maybe thousands of electric cars starting to charge all at once. These things can cause the grid frequency to wobble dangerously fast, much faster than the old system.
So the cleaner the energy mix becomes, the potentially shakier the foundation gets. That feels deeply counterintuitive.
It is. It's the renewable paradox. It's like we enthusiastically swapped out our old, reliable, maybe clunky mechanical clockwork for this super fast, super sensitive digital system. But as one source cleverly put it, we forgot to invent the pacemaker. We didn't build in the mechanism to regulate this new, fast, sometimes jumpy pulse.
Until now. Okay, so this is where the grid-forming inverter, the GFM, comes in. This is the pacemaker.
That's exactly the analogy. GFM is the digital pacemaker. Unlike grid-following inverters, GFM systems don't just follow the grid's beat, they actively create and maintain the beat. They set the frequency, they regulate the voltage, they are the leaders the grid now needs.
Okay, this idea of software mimicking heavy machinery is fascinating. How does it actually work? How does a GFM act as a, what's the term?
Yeah.
A virtual synchronous machine, a VSM.
That's the term, VSM, virtual synchronous machine. And it really boils down to software doing the job that tons of spinning metal used to do. It's about controlling the two key things the grid needs for stability: frequency and voltage. Frequency is about the balance of real power, the energy that actually does work, lights your lights, spins your motors. Voltage is about reactive power. That's a bit trickier. But think of it as the energy needed to maintain the magnetic fields that allow power to flow efficiently. Both need to be rock solid.
And the old generators managed both physically.
Right. Their speed-controlled frequency and other systems managed voltage. Now, inside a Megapack equipped with GFM, you essentially have two interconnected software brains running complex algorithms.
Brain number one.
Brain number one is what you might call the power dispatcher path. This is constantly monitoring the grid, seeing what power is needed right now, and dispatching the real and reactive power from the battery accordingly. It's the workhorse, making sure there's enough juice, correctly formatted, second by second.
And the second brain is the virtual machine part, the VSM magic.
Exactly. That's the virtual machine path. This part specifically simulates the rotational inertia, the flywheel effect. Its algorithms are designed to react instantly to changes in grid frequency. So if the frequency suddenly dips, meaning demand is higher than supply somewhere, this virtual machine path doesn't wait for an external command.
It just acts.
Instantly. It injects a burst of inertial power into the grid. It electronically pushes back against that frequency drop, behaving precisely the way the stored kinetic energy in a giant spinning turbine would have behaved. It damps the fluctuation.
And the key difference here is speed. The sources really hammer this point. We're talking milliseconds for the GFM response.
Milliseconds, maybe even microseconds in some cases. Compare that to a traditional power plant where you might need to physically open valves, burn more fuel, wait for the heavy turbine to actually speed up. That takes seconds, maybe even minutes.
The Megapack isn't just reacting. It's almost predicting and preempting instability before it can even spread.
That's a good way to put it. It's proactive stabilization. And what's really revolutionary, truly game-changing, is this concept of tunable virtual inertia.
Tunable, you mean you can adjust it?
Yes. Unlike a physical turbine, which has a fixed mass and therefore fixed inertia, the GFM's virtual inertia is defined by software code. Grid operators can actually digitally tune it. They can tell the system to behave like a heavier or lighter virtual rotor.
Why would they do that?
To optimize the grid's response for specific conditions. Maybe they know a lot of wind power is about to come offline or a big industrial load is starting up. They can adjust the virtual inertia settings in advance to provide the perfect amount of damping for that expected event. It's making grid stability an intelligent, adaptable property, not just a function of brute physical mass.
Okay, that's seriously impressive on a technical level. But let's bring it back to the real world. Why should someone listening, someone who isn't a power systems engineer, care about virtual synchronous machines and tunable inertia? What are the tangible benefits? This takes us to section 2, real-world resilience and immediate benefits. What's the so what for all of us?
Well, the so what is pretty fundamental. It's about keeping the lights on, keeping society running smoothly. GFM-enabled batteries are shifting how we manage the grid, moving from just reacting to problems to actually preventing them. The most obvious benefit, blackout prevention.
Fewer power outages. Everyone wants that. Can you give us a concrete example where this GFM tech really made a difference?
Yeah, the incident in Hawaii in 2023 is a perfect case study. On the island of Oahu, a huge conventional power plant, something like 208 megawatts, suddenly tripped offline, just dropped out.
Okay, that's a massive loss of power for an island grid.
Huge. Under the old system, without enough inertia, that kind of sudden drop would likely have caused the grid frequency to crash. When frequency drops too low, safety systems automatically start shedding load, basically, causing rolling blackouts to protect the rest of the equipment. You could have seen widespread outages across Oahu.
But that didn't happen.
It didn't, because a large Tesla GFM battery system on the island instantly detected that frequency drop. The virtual machine algorithms kicked in, calculated the exact amount of power needed to counteract the loss, and injected it into the grid within milliseconds. It stabilized the frequency before those automated blackout triggers could even fully activate.
Wow. So it didn't just respond, it prevented the cascade. It kept the system stable through a major shock. That's not just backup power, that's active grid orchestration.
Precisely. It's maintaining the rhythm of life, as you said earlier.
Yeah.
And this ability to provide continuous stability, it has massive knock-on effects for cost and efficiency, too.
No.
Think about continuous operation for the remaining conventional power plants. Fossil fuel plants, especially older ones, they really don't like being ramped up and down constantly to follow the fluctuating output of solar and wind. It's inefficient, burns extra fuel, and causes a lot of wear and tear, leading to higher maintenance costs.
Right. They prefer to run steady.
Exactly. With large GFM batteries like Megapacks handling the moment-to-moment balancing, soaking up excess renewable energy and filling the gaps, those conventional plants can often be run at a much steadier, more optimized output level. They become more efficient, they need less maintenance, and they actually produce fewer emissions because they aren't constantly gunning their engines, so to speak.
So the battery helps the other power plants run better too.
Yeah.
That's interesting.
It absolutely does. And then there's the ultimate resilience test, the thing that used to be the exclusive domain of only the biggest, most robust power plants, black start capability.
Restarting the grid after a total collapse. The nightmare scenario.
Yeah, bringing an entire region's power grid back online from a complete blackout from zero. It's incredibly complex. Traditionally, you needed a specific type of power plant with its own internal power source to generate that initial, stable electrical signal that everything else could then synchronize to.
Like jump-starting a car, but for an entire state or country.
Kind of, yeah. But GFM-enabled battery systems can do this now. They can provide that initial, clean, stable frequency and voltage reference signal using stored energy. They can essentially form the grid from scratch, allowing other power plants and grid sections to be brought back online in a controlled, sequential way. It can potentially turn what could be days of restoration work into a much faster, more automated process. Huge for energy security.
It sounds like Prometheus bringing fire back to humanity, but with algorithms.
That's not a bad analogy, actually.
And we've seen this proven in practice, right? Australia's Hornsdale Power Reserve often gets mentioned as the pioneer here.
Hornsdale is the classic example. It started as just a very large battery, doing energy arbitrage, buying low, selling high. But then it was upgraded with grid-forming capabilities. And shortly after, there was a major incident. A fault on a big transmission line connecting different states. A nearby coal plant, which was supposed to help stabilize things, didn't respond correctly.
And Hornsdale stepped in.
Instantly.
Yeah.
The GFM software detected the instability, the frequency wobbling, and injected the precise amount of power needed to stabilize it. The correction happened in under 200 milliseconds.
0.2 of a second. That's incredibly fast.
It's faster than the blink of an eye. It fundamentally demonstrated that batteries with the right software could outperform traditional generators in providing these critical grid stability services. And it gave regulators the confidence to rely more on batteries and less on aging fossil fuel plants for grid security.
And Australia isn't just doing one-offs. They're really leaning into this, aren't they?
Oh yeah, they're basically mandating it now. The Australian energy market operator is actively pushing for, I think the target is 4.5 gigawatts of dedicated grid-forming storage capacity by 2026. That's a massive national commitment. It shows this isn't seen as experimental anymore. It's viewed as essential infrastructure for grids that will have lots of wind and solar.
And we saw a similar story with the Kapolei project back in Hawaii.
Kapolei is another great example. That battery system directly replaced Oahu's very last coal-fired power plant. And it wasn't just a simple swap. The battery system took over essential grid services like frequency response and, significantly, black start capability. It proved, especially for isolated island grids, that renewables paired with smart grid-forming storage can reliably replace traditional baseload power. More flexible, too.
Okay, so wrapping up the benefits economically, this invisible infrastructure, as you called it, it pays dividends beyond just enabling renewables.
Absolutely. Grid instability is expensive. Utilities can face huge financial penalties if they can't maintain frequency within tight bounds. They also have to pay for spinning reserves, keeping old gas plants idling just in case they're needed for stability. GFM batteries drastically reduce or eliminate these costs.
Saving millions.
Millions, potentially billions across a large grid. Plus, they reduce the need to fire up expensive peaker plants that only run a few hours a year during high demand, usually burning natural gas. And here's a big one. By providing stability locally, these battery systems can often delay or even completely avoid the need for incredibly expensive, time-consuming upgrades to the physical transmission lines. That saves ratepayers a fortune and avoids years of construction hassle. It's often the smartest grid investment you can make right now.
Right. It's like upgrading the traffic control system instead of building 10 new lanes of highway.
That's a perfect analogy. More intelligence, less concrete.
Okay, so we understand the tech, the benefits, the real-world impact. But Tesla, while a pioneer, isn't alone. This is a massive global market taking shape. Who else is building these digital hearts for the grid? Let's shift gears into Section 3. Megapack versus the world. The geoeconomics of electrons.
Yeah, this is where the technology story crashes headlong into global economics and politics. For the last half-century, maybe longer, geopolitics revolved around oil barrels. Who had them? Who controlled the shipping lanes? Now the focus is shifting to stored energy programmable electrons, digital oil, whatever you want to call it. And the race to build the infrastructure for that is intense.
Tesla obviously has a strong brand and that early mover advantage in the software. You mentioned they have about 15% of the global market share for integrating these big systems.
Roughly, yeah. As of recent figures, they set a high bar early on, especially with the intelligence layer, the GFM software. But the market is incredibly dynamic. And honestly, it's currently dominated in terms of manufacturing muscle by players from the East.
Specifically China.
Overwhelmingly, if you look at the top 10 companies integrating these large-scale battery storage systems globally, 7 of them are Chinese. They effectively shape the economics of the entire lithium-ion supply chain, from mining the raw materials to assembling the final battery packs.
Okay, let's break down some of these major players. The biggest name in batteries overall has to be CATL, right? Contemporary Amperex Technology.
Absolutely. CATL is the world's largest battery manufacturer, period. Their superpower is massive scale, vertical integration, and relentless cost reduction. They supply the core battery cells to many companies, including some of their Western competitors.
And they're big on a specific battery chemistry.
Yes, LFP lithium iron phosphate. It's become the dominant chemistry for grid-scale storage because it's generally cheaper to make, it's considered safer, less prone to thermal runaway, and it lasts for more charge cycles than the older nickel, manganese, cobalt, NMC types, even if it's a bit less energy dense. CATL's sheer scale in LFP production basically sets the price floor for the entire industry.
Okay, so CATL makes the cells. Who's their biggest rival in putting the whole system together, the integration part? Often Sungrow comes up.
Sungrow is right up there. They're number 2 globally in system integration, holding maybe 14% market share, neck and neck with Tesla in that regard. Sungrow's background is actually in inverters. They were already a world leader in solar inverters before getting big into storage.
Ah, so they have deep expertise in the power electronics side.
Exactly. That gives them a huge advantage in developing their own sophisticated grid-forming capabilities and deploying systems quickly and reliably. They're arguably Tesla's strongest direct competitor when it comes to the overall system intelligence and performance, particularly in markets across Asia and Europe where they have a strong presence.
Then you have another Chinese giant, BYD, Build Your Dreams. They seem to do everything.
They practically do. BYD is famous for its extreme vertical integration. They're involved in everything from materials processing right up to building electric cars and buses, and of course, massive grid batteries. Their unique selling point is often their blade battery design.
What's special about that?
It's an LFP battery, but the cells are designed as long, thin blades packed very efficiently and safely. BYD emphasizes the safety and reliability aspects, which gives them a strong foothold, especially in emerging markets or places where maybe grid conditions aren't always perfect and you need something really robust.
And we can't ignore the tech behemoth that's moved aggressively into energy, Huawei.
Right, Huawei Digital Power. They've come on strong, leveraging their deep expertise in power electronics from their telecom business and their massive global sales and service network. They offer very competitive, complete turnkey solutions. If you're in a country that already uses a lot of Huawei networking gear, their energy solutions can be an easy fit.
So when you add up CATL, Sungrow, BYD, Huawei, and the other Chinese players, what does that dominance look like strategically? What are the projections for, say, 2030?
It's pretty stark, honestly. The projections suggest that this China bloc collectively could be responsible for somewhere between 50% and 65% of all global grid-scale battery deployments by 2030.
Wow, potentially two-thirds of the market.
Yeah. And remember, they also control something like 70% of the world's lithium refining and close to 80% of battery cell manufacturing capacity. So you have this situation where the technology that's supposed to deliver energy independence for many Western countries is, right now, highly dependent on Chinese supply chains. It's a major strategic vulnerability.
A definite paradox, as you said. So given that reality, how are the Western players, the non-Chinese companies, competing? Where's their focus?
Well, besides Tesla, the other major Western integrator is Fluence. That's a joint venture originally formed by Siemens, the German industrial giant, and AES, a big American power company.
What's Fluence's angle?
Their strength tends to be in sophisticated software platforms for controlling and optimizing these battery assets, and crucially, they have a high degree of trust with Western utilities and regulators. They've contracted or deployed something like 18 gigawatts globally. In a world where supply chain security and, frankly, geopolitics are increasingly important, being a non-Chinese option with strong software is a key advantage, especially in the US and Europe, where diversification is becoming policy.
And we shouldn't forget the established battery makers from South Korea, right?
Definitely not. LG Energy Solution and Samsung SDI. These companies are veterans in high-quality battery cell manufacturing. They've been doing it for decades for consumer electronics and electric vehicles.
So they bring reliability and quality.
Yes, proven track records. And they are major beneficiaries of the push for localization in the West. Both LG and Samsung are building huge new battery factories in North America and Europe, often backed by government incentives like the U.S. Inflation Reduction Act. Their costs might currently be higher than the big Chinese players, but for Western buyers looking to diversify, they are critical partners.
So it seems the new energy race isn't just about finding oil anymore. It's about controlling lithium mines, mastering chemical processes, building gigafactories at scale, and writing the smartest control algorithms.
That's it, exactly. The entire value chain is the strategic battleground now. And the market itself is just exploding. The forecasts are wild. We're looking at the global grid-scale battery market potentially growing from around, say, $48 billion in 2025 to over $240 billion globally by 2035. That's a five-fold increase in just 10 years. The new industrial empires aren't being built on oil fields, they're being built on data centers running AI to manage grids, and the mines and factories that supply the batteries.
That scale of change is mind-boggling, and it points to something deeper than just market share. The grid itself is fundamentally changing its nature. It's becoming less like a machine and more like something else.
This leads us perfectly into Section 4, the energy internet. From smart grid to sentient infrastructure. What does that even mean?
It means we're moving beyond the idea of a smart grid, which was mostly about adding sensors and some automation to the old system. We're heading towards what some thinkers are calling a sentient infrastructure. Think of it less like plumbing and more like a biological nervous system, or even a global brain for energy.
Okay, break that down. A global brain. Imagine it this way. All those millions of solar panels and wind turbines, they're like sensory neurons, constantly detecting energy from the environment. And the Megapacks, the Sungrow units, all these GFM batteries, they're like the synapses. They receive those energy pulses, they store them, they regulate them, and crucially, they compute and decide where to route them almost instantly based on information flowing through the network.
Synapses that think.
Kind of, yeah. It's an active, intelligent network. And our sources suggest we can think about this emerging energy internet in terms of four distinct layers building on each other.
Okay, let's start at the bottom. Layer 1.
Layer 1, the physical layer. This is the battery web. It's the growing physical mesh of all these grid-forming batteries being deployed everywhere. Not just huge utility plants, but maybe community batteries, industrial site batteries, eventually even clusters of home batteries acting together. They're getting bigger, too. We're seeing plans for single sites holding 10 gigawatt hours, GWH or more.
10 GWH, that's enormous.
Massive. But the key point is they aren't just passive storage tanks. They function as energy routers. They're active nodes in the network, constantly sensing grid conditions, predicting short-term changes using local data, and autonomously deciding when to charge, when to discharge, and how to modulate their output to maintain stability. They're routing power intelligently.
Okay, so you have this web of intelligent batteries.
Yeah.
How do they talk to each other? How do they coordinate? That must be the next layer.
Exactly. Layer 2, the digital layer. This is the neural network overlaying the physical web. This is where advanced software, particularly AI and machine learning, takes over from traditional, often manual grid control systems.
AI running the grid.
More and more, yes. AI algorithms are getting incredibly good at forecasting energy demand and renewable generation, sometimes hours or even days in advance, with high accuracy. They can predict potential bottlenecks or instabilities before they happen. But for this to work across systems built by different companies, you need common languages, communication standards.
Like internet protocols, but for energy.
Precisely. Things like IE 2030.5 or OpenADR. These protocols allow a Tesla Megapack in California to potentially coordinate its actions with, say, a Sungrow battery in Nevada, or even theoretically, a Fluence system in Germany, all communicating securely over the internet using standardized messages about grid needs and available capacity.
That level of coordination is mind-blowing. It implies you could balance energy not just locally, but across continents.
That's the ultimate vision. Imagine it. Peak solar generation happening in the Gobi Desert, charging massive battery farms there. Hours later, as the sun sets in Europe, those batteries could be discharging, sending power west via ultra-high voltage lines, coordinated by AI to meet European evening demand. It's a continuous, optimized, global energy handshake managed by algorithms to maximize efficiency and minimize waste.
Okay, physical web, digital neural network. What's layer 3?
Layer 3, the cognitive layer. This is where things get really interesting, maybe even a bit philosophical. This is where the system starts to exhibit grid consciousness, or at least collective intelligence.
Grid consciousness. That sounds like science fiction.
Well, maybe not consciousness like ours, but emergent intelligence. When you have millions of these smart, interconnected devices, batteries, solar inverters, smart thermostats, EV chargers, all constantly sensing, communicating, and reacting according to programmed rules and learning algorithms, the entire grid can start to behave in ways that look surprisingly intelligent.
How so? Give me an example.
Okay, think about a major grid stress event, like an extreme heat wave driving up demand while some power lines are down due to wildfires. A cognitive grid, potentially driven by AI, could make complex trade-offs automatically. It might prioritize keeping power flowing to critical infrastructure, hospitals, emergency services, cooling centers, while perhaps temporarily curtailing power to less critical high-consumption loads, maybe like large industrial users who've agreed to such interruptions, or even dynamically adjusting prices to discourage non-essential use.
So it's making value judgments based on preset priorities, almost ethical decisions.
In a way, yes. It's executing a complex balancing act based on rules and real-time data that go beyond just keeping the frequency stable. Stability in this cognitive grid emerges from the bottom up, from the interactions of all these distributed intelligent agents, rather than just being dictated from a single central control room. This is what engineers mean when they talk about making the grid anti-fragile.
Anti-fragile, meaning it gets stronger from shocks.
Exactly. Like a biological immune system, it doesn't just resist failure, it learns from disturbances, adapts its strategies, and potentially becomes even more resilient over time because the intelligence is distributed and learns collectively.
Which brings us inevitably to the human side of all this, layer 4.
Layer 4, the ethical layer. This forces us as a society to define the new social contract of power for this digital energy age. As the grid becomes decentralized, data-driven, and increasingly autonomous, really profound questions pop up. Like, who owns the incredibly detailed energy usage data generated by your smart meter, your electric car charger, your home battery? Who gets to decide when the utility can draw power from your home battery to help stabilize the grid? And how are you compensated? If an AI makes a decision during a crisis that cuts power to one neighborhood to save another, how is that decision audited? What are the rules for transparency and accountability when the grid itself starts thinking?
Yeah, those are huge questions. We need to figure out the governance before the AI gets too sophisticated.
Absolutely. We need to embed our societal values into the code, into the protocols, into the market rules that govern this energy internet.
So, stepping back, the big philosophical shift you're describing is
Well,
from mass to information.
that's the heart of it. The 20th century grid found its stability in mass, the sheer physical inertia of giant spinning machines. The 21st century grid finds its stability in information and data, algorithms, computation, communication, and digital inertia. That megapack sitting out there isn't just a dumb box of chemicals. It's a powerful computer, constantly sensing, thinking, predicting, and reacting.
And that intelligence, that ability to manage intermittency, is what finally unlocks the full potential of the most abundant energy source we have.
Precisely. It allows us to harness the power of the sun on a scale previously unimaginable.
Perfect segue. Let's talk about where all this clean energy is actually going to come from. Section 5. The Great Solar Awakening Powering Civilization with Deserts. If the battery is the brain, the deserts are the powerhouse.
They really are. For so long, our energy thinking was literally grounded, looking down for coal, oil, gas. But now we're realizing the most immense energy reserves are actually above us, bathing the planet in sunlight every day. And deserts are the prime collection zones.
The numbers are staggering, aren't they?
They are almost hard to comprehend. Our sources consistently point out this fact. A typical square kilometer of sunny desert receives more solar energy in just about 6 hours than the entire human population consumes in all forms in a full year.
Wow. Let that sink in. 6 hours of sunlight on 1 square kilometer equals a year of global energy use.
Yeah. The energy is there in unbelievable abundance. The challenge was always capturing it efficiently and, crucially, storing it and stabilizing it so we could use it when the sun isn't shining. That's where grid-forming storage changes everything.
So GFM batteries enable what you're calling the era of solar sovereignty.
I think that's a good term for it. It means regions, even entire nations, can potentially generate, store, and manage their own clean power supply, 247, derived largely from sunlight falling within their own borders or nearby. It's a fundamental shift away from dependence on geographically concentrated fossil fuels, which have driven so much conflict and instability.
And we're already seeing the blueprints for this new solar world map being drawn, focusing on these massive desert hubs. Let's start with maybe the most ambitious vision: the Sahara for Europe.
The Sahara Desert is just this perfect, vast solar collector, 9 million square kilometers, intense sunlight, very little cloud cover. The idea of harnessing it for Europe isn't new, but it's becoming much more realistic now.
With projects like Desert Tech 2.0 and that X-Links project from Morocco to the UK.
Exactly. These projects involve laying incredibly long, high-capacity, high-voltage direct current HVDC cables. These aren't your standard AC transmission lines.
Yeah.
HVDC can transmit enormous amounts of power over thousands of kilometers under the sea or across land with surprisingly low energy losses.
So giant solar farms in Morocco or Algeria, connected by HVDC cables under the Mediterranean or the Strait of Gibraltar, feeding power directly into the European grid.
That's the plan. We're talking about potentially 10 to 15 gigawatts of power flowing along these corridors, but, and this is critical, you absolutely need massive grid-forming battery installations at both ends.
Why at both ends?
At the generation end, in North Africa, you need huge batteries, maybe 5 to 10 kWh clusters, to smooth out the solar output, store excess power, and create that stable grid-forming signal to inject into the long HVDC line. At the receiving end, in Europe, you need similar large GFM batteries to receive that power, ensure it integrates smoothly with the European grid frequency, and provide inertia and voltage support locally. The batteries make the whole intercontinental transmission feasible and stable.
This literally redraws the energy relationship between continents. North Africa becomes a green energy superpower, exporting sunlight to Europe.
Potentially, yes. The forecasts are bold. Some suggest Europe could be importing 30% or even 40% of its total renewable electricity from North Africa via these corridors by 2040. It's a vision of interconnection based on light, not gas pipelines.
Okay, let's look east. Rajasthan for India. Another massive desert, right? The Thar Desert.
Yeah, the Thar Desert has some of the highest solar irradiance levels anywhere on Earth, and India has incredibly ambitious renewable energy goals, aiming to become a 247 solar nation.
How are they planning to achieve that?
By building truly enormous solar parks, some exceeding 20 gigawatts in single regions like Rajasthan. But again, the key isn't just the panels, it's the storage needed to make that solar power useful around the clock.
So big battery hubs are essential there too.
Absolutely. India is investing heavily in domestic battery manufacturing and deploying storage hubs ranging from 1 GWh up to 10 GWh alongside these solar parks. These batteries will absorb the massive daytime generation and discharge it through the evening and night, ensuring that India's growing electricity demand can be met increasingly by stored sunlight. The goal is audacious. Some projections see Rajasthan alone potentially supplying 40% of India's total national electricity needs by 2035, largely from solar plus storage. That's real energy independence taking shape.
Incredible. Now let's swing over to North America, the Arizona for America concept, focusing on the U.S. Sunbelt.
Right, the American Southwest, Arizona, Nevada, California, Texas, it's blessed with abundant sunshine, over 300 sunny days a year in many areas. The vision here involves creating solar interstates.
Solar interstates, like highways for electrons.
Yeah. Kind of, yeah. Imagine vast solar arrays built along major sun-drenched corridors, like alongside Interstate 10, connected by high-capacity transmission lines feeding into absolutely enormous battery storage centers.
And the scale of storage being planned there is even bigger.
The numbers are staggering. We're seeing proposals for integrated storage facilities reaching 100 kilowatts of capacity, designed to anchor the stability of the entire western U.S. grid. This concentration of solar generation and massive GFM storage could turn the Southwest into, as some call it, the Silicon Valley of sunlight.
And the long-term goal for the U.S.
The really ambitious targets, supported by policies like the IRA, aim for solar power, backed by storage, to potentially provide as much as 80% of all U.S. electricity by 2045. That kind of penetration is only possible if you have widespread grid-forming storage providing the foundational stability.
And this desert-powered vision isn't limited to these three regions, is it?
Not at all. It's a global pattern. China is aggressively developing solar and wind in the Gobi Desert, aiming for perhaps 200 GW of capacity by 2030, tightly integrated with their domestic battery giants like CATL. Australia's ambitious Suntable project aims to build a massive solar farm in the outback and transmit 3.2 GW of power via a 4,000-plus kilometer undersea HVDC cable all the way to Singapore.
Wow.
And Chile, leveraging the incredible solar resource of the Atacama Desert, is on track to have its grid run on nearly 100% renewable energy by 2035, again, heavily reliant on storage and sophisticated grid controls. Everywhere you look, deserts plus batteries plus smart grids equals the future of energy.
It's undeniable. The energy map of the 21st century is being drawn by sunlight, silicon, and lithium, which brings us squarely to the global power dynamics. Let's pivot to Section 6, Power Diplomacy 2.0, the geopolitics of storage. How does this new energy reality change the global strategic game?
Fundamentally, utterly, the entire basis of geopolitical power for the last century was, to a large extent, tied to oil. Who had it? Who controlled the narrow straits it passed through, like Hormuz or Suez? Wars were fought over this stuff.
The great game played with pipelines and tankers.
Exactly. Now, the 21st century game is about controlling different choke points. The supply chains for critical minerals like lithium and cobalt, the advanced manufacturing capacity for batteries and semiconductors, and maybe most importantly, the algorithms and AI that manage the flow of electrons on these increasingly complex grids. As one analyst put it quite brilliantly, the new OPEC will be made of algorithms and electrolytes.
Algorithms and electrolytes. I like that. So how are the major world powers positioning themselves in this new game? Let's look at their strategic approaches. China.
China's strategy seems focused primarily on muscle power, on industrial dominance. As we discussed, they control a huge chunk of the critical mineral processing, around 70% of lithium refining globally, and an even larger share of battery cell manufacturing, maybe 77% or more. Their Belt and Road Initiative is increasingly becoming an energy Silk Road, where they offer partner countries not just infrastructure loans, but entire packages of solar farms, wind turbines, and the crucial battery storage systems needed to make them work, often supplied by companies like CATL or Sungrow. Their power comes from scale, integration, and controlling the physical supply chain.
Okay, so China's got the manufacturing muscle. What about the United States? Given that manufacturing deficit, where's the U.S. focus?
The U.S. strategy appears to be leaning more towards the brains of the operation. While there's a huge push through things like the Inflation Reduction Act, or IRA, to onshore more manufacturing and secure domestic supply chains aiming for maybe 50% localization by 2030, the real competitive edge the U.S. is banking on seems to be in software, artificial intelligence, and those advanced grid-forming algorithms.
So leveraging the tech innovation from Silicon Valley and companies like Tesla, Fluence.
Exactly. The idea is that even if the physical battery cells might come from elsewhere initially, the U.S. can lead in creating the sophisticated operating systems, the AI-driven optimization platforms, the cybersecurity protocols that make these energy systems truly smart, efficient, and secure. The export strategy becomes less about selling boxes and more about selling the intelligence embedded within them.
Interesting contrast. Muscle versus brains. Now, what about Europe? Especially given their recent, very painful wake-up call regarding dependence on Russian gas.
Europe's strategy is heavily driven by the desire for autonomy and decentralization. There's massive investment going into building a European battery alliance, creating their own gigafactories, developing sustainable battery chemistries, reducing reliance on imported cells. Simultaneously, they're pushing hard to build a truly interconnected, resilient pan-European supergrid.
And connecting that grid southwards.
Yes, connecting to those North African solar resources via HVDC is a key part of the plan. The dual goal is clear. Break free from dependence on Russian fossil fuels and avoid simply swapping that for dependence on Chinese clean energy technology. It's about achieving strategic energy autonomy through a combination of domestic manufacturing, continental grid integration, and diversified import sources like Saharan solar.
And where does India fit into this picture? They seem uniquely positioned.
India's fascinating. Geographically and politically, they sit at a crucial crossroads. With their massive domestic energy needs, huge solar potential, and rapidly growing manufacturing ambitions, they are emerging as a potential energy balancer, maybe even a swing producer in the global clean energy system.
Just swing producer. Like Saudi Arabia was for oil.
Potentially, in the sense that their choices could significantly influence global markets. They are attracting enormous investment and technology transfer from both the US, Europe, and China, playing them off against each other to some extent. If India successfully builds out its own massive solar and storage capacity and develops a strong domestic manufacturing base, it could gain significant geopolitical leverage as a large, relatively non-aligned hub in the clean energy world.
So as batteries and storage become these core strategic assets, we're seeing new kinds of alliances form, right? Not like the old OPEC model.
Exactly. The new alliances look less like resource cartels focused on restricting supply and more like technology partnerships or infrastructure agreements, almost like cloud computing deals. You see things like the US-EU Energy Security Council working on secure supply chains and maybe coordinating storage strategies. There are talks about the IMEC corridor, India, Middle East, Europe, potentially becoming a major route for transmitting clean energy and requiring coordinated storage investments.
And maybe even within the BRICS group.
There's definitely potential there. You could imagine a BRICS plus battery bank emerging, pooling lithium resources from South America, battery manufacturing from China and India, and financing capabilities to build storage infrastructure across the global south, creating an alternative ecosystem to the Western-led initiatives.
This really signals a profound shift in what constitutes national power. You mentioned moving from petrostates to electrostates.
That's a term gaining traction. Petrostates derived their power, often immense power, from controlling scarce, geographically limited resources, oil and gas. Their influence came from scarcity. Electrostates, on the other hand, will derive their power from harnessing abundant resources, primarily sunlight and wind, and mastering the technologies to store, manage, and share that energy efficiently. Their power comes from abundance, intelligence, and interconnection.
Can you give examples of potential electrostates?
Well, think about Australia, with its vast deserts and coastline. It could become a primary global battery mine and solar farm, exporting both raw materials and finished energy products like green hydrogen or direct electricity via cable. Or consider the lithium triangle in South America, Chile, Bolivia, Argentina. If they can manage their resources effectively and move up the value chain, they could become the energy storage equivalent of what Saudi Arabia was to oil. Sovereignty in this new era isn't just about territory. It's increasingly about energy intelligence. Who controls the GFM algorithms? Who manages the data? Who ensures the stability of these complex interconnected systems? That's where real power will lie.
So the Megapack and all its global competitors, they aren't just industrial products. They are, in effect, strategic geopolitical assets shaping the 21st century.
They absolutely are. They dictate who has energy security, who benefits from the clean energy transition, and where economic power concentrates. But there's also a potential upside, a paradox perhaps. Because the primary fuel source, sunlight, is so widely distributed, unlike oil, this transition could potentially lead to a more balanced, less conflict-prone world. If energy can be generated locally almost anywhere and traded efficiently through interconnected grids stabilized by storage, maybe the zero-sum competition over scarce resources becomes less intense. Energy security shifts from defending oil wells to defending data networks and ensuring grid intelligence. It offers a path, at least, towards peace through balance.
Okay, that's a hopeful note. Let's try to pull all these threads together, synthesize the main takeaways from our deep dive today. What's the core message?
The core message, I think, is that the Megapack and the broader revolution in grid-forming storage it represents is fundamentally transforming energy. It's shifting it from being primarily a commodity of mass, physical tons of coal, barrels of oil, into becoming a commodity of information. It's about data, it's about AI, it's about programmable stability delivered by sophisticated software controlling powerful hardware.
Right. The physics is changing from mechanical inertia to digital inertia.
Exactly. The 20th century was defined by combustion and the brute force of inertia. The 21st century is being defined by intelligence, feedback loops, and computation. We're literally building an energy internet, moving away from a rigid, brittle machine towards something more like a collective, self-healing, anti-fragile organism. And grid-forming technology, GFM, is the critical enabling piece that allows this complex, renewable heavy system to actually work reliably.
The sheer scale of it all, from the tiny transistors managing the algorithms inside a GFM inverter, all the way up to these planned 100 GW battery fortresses stabilizing entire regions from desert solar farms. It's just breathtaking. It's the new architecture for civilization, really.
And we are still just in the early days of this great solar awakening, as you called it. As energy becomes increasingly programmable, distributed, and intelligently managed, you can see civilization itself starting to operate more like a vast, self-balancing system. A constant interplay of energy generation, storage, computation, and adaptation.
Okay, so to wrap things up, we always like to leave our listeners with a final provocative thought to chew on. What should people be thinking about after hearing all this?
Well, think about this. The loud roar of the giant turbines in those old power plants is fading. That rhythm of combustion and scarcity that defined the last century is going quiet. But if you listen very carefully now, especially near one of these new battery installations, you might just hear the very faint, soft electronic hum of the Megapack or its competitors. Thinking, computing, balancing.
The sound of digital inertia.
Exactly. And that quiet hum, that's arguably the sound of Civilization 2.0 booting up. It's the sound of a global energy nervous system learning to operate, a system where power itself, enabled by intelligence, might finally learn to flow, not to fight. It's a system where the stability of our future might, for the first time, be rooted not just in heavy metal, but in distributed intelligence.